Welcome to this presentation. My name is Olof Mogren, and I'm presenting joint work with John Martinsson, Edvin Listo and Daniel Gillblad. The topic of this presentation is adversarial representation learning for synthetic replacement of private attributes. This smile does not exist. This title is a tribute to websites such as "This person does not exist" and "This climate does not exist." They use similar technologies as the one I will present here today. But instead today, we're talking about privacy. We're talking about privacy for image features, which can give you a privatization mechanism that works on dataset level. We'll also touch a little bit upon the trade-offs between utility and privacy in this setting. Well, consider the images that you have in front of you. We see a man and a woman, and we see them in two different versions. Well, these versions were passed through our privatization mechanism, where the sensitive attribute was being whether the person smiles or not. So please take a couple of seconds to think about whether you think the original image of the man was a smiling man and whether the woman was a smiling person. I'll give you the true answer. The man was smiling in the input image and the woman was not smiling in the input image. So these images are from the Celeb A dataset, and the smiling is one of the attributes that were tagged in this dataset. We'll mention a couple more attributes in a minute, but we'll actually touch more on the smiling attribute because it's actually a quite interesting one. What pixels hold a smile? Well, the mouth is important for a smile, possibly the most important. But the more you think about it, you start to think about other features as well. So eyes certainly change, dimples may occur, wrinkles may appear in the face. And there has been some strategies to privatize images, such as blurring or removing or replacing parts of the image. But O et al. In 2016 showed that blurring or removing has a limited effect on privacy of the facial images. So we actually have to start to disentangling the underlying factors here, which is a really challenging task. Generative adversarial privacy was presented by Huang et al. In 2018. They presented a model based on conditional generative adversarial networks to filter images. So for an input image X, they produce an output image X prime, where some sensitive features have been filtered out. And the objective for this is that they train an adversary at the same time. And the task for the filter is to make it hard for the adversary to find out the value of the sensitive attribute. For this, you need to specify the sensitive features and you give the model a distortion constraint. So the current work builds on the generative adversarial privacy framework. But in our case, we propose a two-step process. So we train a filter model in similar sense, but then we add a generator model. And the generator takes as input the output from the filter. It also has a second input, which is coined S prime here. And S prime is a random variable that's sampled independently from the input X. Now, we consider sensitive attributes which are binary here. So in that sense, S prime is also binary, and it determines the value of the sensitive attribute that the generator has to generate. So the output from the generator is then an image which contains either of the two values of the sensitive attribute. So for smiling, that would be if the person either smiles or not smiles. Whereas the output of Huang et al. Produces something that's difficult to determine whether it's smiling or not. In our solution, both the filter and the generator are based on the UNet architecture. And the approach assumes no knowledge about the downstream task. So, learning objectives. In front of you, you see 3 different versions of a plot. We have synthetically generated data with 2 different means. These are 2-dimensional Gaussians. So the orange crosses are corresponding to the sensitive attribute being 0, and the blue points correspond to the sensitive attribute being 1. We have also fitted a linear classifier to classify these 2 classes. The classifier can be seen as the adversary in this case, and we have illustrated with small arrows the gradient for the objective. Leftmost plot shows the case where we're minimizing the log likelihood of the adversary, and this is used as a baseline in our work and is inspired of the work by Huang et al. The circle you see around the highlighted point is the distortion budget. And the arrow is following the gradient as long as it can until it is being stopped by the distortion budget. In the middle picture, you instead see what happens when you maximize the entropy of the adversary. And here you can see that we're instead moving closer to the decision boundary. We're not going all the way to the distortion budget constraint, but instead we're going towards the decision boundary. And this is to make the adversary as uncertain as possible. The rightmost plot contains the proposed method. Here, we're taking a step towards the decision boundary as proposed by maximizing the entropy of the adversary, and then we're sampling a random direction, either towards s equals 0 or towards s equals 1, depending on the independently sampled s prime attribute. So, implementing these methods on this synthetic data, we see the following. So we still have the orange crosses and the blue dots here, but then we have in the leftmost plot we have red color for the transformed data points. So if we're using the log likelihood of the adversary and maximizing that to transform the data, we get something similar to the leftmost plot here. And the clusters of data points are actually still fairly easy to classify into crosses and dots. In the middle plot, where we're maximizing the entropy of the adversary, the data points have rather collapsed. So you can see a small cluster of data points in the middle with the green color, and those are the transformed points. Now, with our 2-step approach, in the rightmost plot here, you can see that the transformed points and crosses, which are purple, they are showing much of the global configuration as the input data, but they are actually scrambled. So, to some qualitative results. These are images where we have transformed the smiling attribute. We have 4 different images, and the leftmost 4 of them have the distortion constraint of 0.001. The rightmost 4 images have the distortion constraint of 0.01. The first line is the input image. The second line is transformed by the baseline method. The third line is transformed by our method and is generated in non-smiling. And the fourth line is transformed by our method and has a synthetic smile. So as you can see here, the baseline method continuously produces outputs that's more blurry and more garbled than our method. And if you concentrate on this column, you can see that our method on line 3 and line 4 produce realistic looking samples, which are much more clearer than the baseline, and which hides the sensitive attribute in being either of these samples. So for some quantitative results, here we have the trade-offs between privacy loss and utility score. So x-axis is privacy loss and the y-axis is utility score. You can see the baseline in solid red, which is following for the 4 different values of distortion budget that we have examined here. It consistently, more or less, performs worse than the other methods. The baseline method with the entropy loss is getting slightly better scores for most of the points. Our method in the dashed green line consistently outperforms all other methods, including our ablation with the log likelihood, which is the solid green line. Top left is the best here, and you can clearly see that the results here is always a trade-off between the privacy and the utility. The more you garble the image, the more private it will be. Thank you all for listening to this talk.